Thank you for joining us for this 30-minute webinar on optimizing electrode slurries via Rheo-Impedance Spectroscopy. Today's presenter is Dr. Lucas Schwab, an application support engineer in mechanical testing at TA Instruments. Lucas specializes in rheometers, DMA, and rubber testing, serving as the contact person for all questions related to these techniques and helping users get the most out of their instruments. Without further ado, I'll turn it over to Lucas to start the webinar.
Thanks a lot, and also from my side, a very happy welcome to you to this fourth part on this webinar series. And in this webinar, I want to show you how the combination of impedance spectroscopy and mechanical rheological testing of electrode slurries can give you more deeper insights into the structure of these slurries. So first of all, why is this important? So I guess as all of you know, modern electrodes of lithium-ion batteries are composed of a lot of different ingredients. So we have the different active materials, the conductive additive, and the binder, and they all together form these electrodes, be it the cathode or the anode. And these electrodes need to fulfill a lot of different properties to get the optimum performance. So, for example, we need a very homogeneous surface of the electrode, so no holes, homogeneous thickness. We need good adhesion both within the electrode, but also between the electrode and the current. But of course, we also need to ensure good electrochemical control. So what we want to focus today on is to have a deeper look into the electrical conductivity of our electrode and the slurry, and how we can check that at a very early stage and relate this to the final performance of our battery. So basically, we focus on the properties of the conductive additive in our slurry, which is typically carbon black or a similar carbon product like graphene or carbon nanotubes. So here we just have a short recap of the production process of such an electrode. So we have all the different ingredients that we need. So active material, conductive additive, and binders combined together, and then typically in a liquid media to form a liquid slurry, but of course this can also be a dry slurry. We mix them together, bring them to the coating area, where then a thin layer of this slurry is coated on the metal collector, and then we put the electrodes to the drying and have our final electrode, which is then assembled into the different cells, packs, and then the final modules. So when the typical analysis that we can do are for the final the important analytics are at the final stage. For the battery, it's electrical properties, but because this is what the application is made for, so therefore this is in the end one of the major points they must fulfill. And their dielectric or impedance spectroscopy is a major technique to get information about the electrical behavior of these materials. But if we look more on the slurry stage, then the mechanical behavior of the slurry is important. So how fast can we coat it? How do we achieve the best mixing? How fast or how long do we need to wait between the coating and the drying so that we get a smooth surface of our electrode and things like that? That is all determined by the mechanical behavior of the slurry, and therefore we need methods like viscosimetry or rheology to determine these mechanical processes. So here we have two different analytical technologies that are also mostly used on different stages of our um, of the production process of a rheometer, but by of a cell. But by combining these two methods together in one experiment, we hopefully can get information about the final behavior of our cell already at an early stage from the slurry. So this is the whole intent of this new setup that we have, or this combination of rheology and impedance spectroscopy, is to get information about the electrical properties as soon as possible in the production process to improve the performance of the final battery without always going through all the steps to produce a complete battery. So just a short recap, what is rheology doing? So in rheology, we have an instrument that is that has a motor which applies or which moves a certain geometry. So in this case here, the top geometry, and we measure how much force or torque is needed for that movement, and by that we get information about the viscosity and the modulus of the sample. So there are two common kinds of tests that are used on a rheometer. So on the left side we see flow tests. So by a flow test we mean that the top geometry is rotated at a certain speed or shear rate, and we determine the viscosity at that shear rate. So this is a large movement of the geometry in one direction, and typically used to simulate different processing conditions and getting information about the viscosity under certain conditions, like certain shear rates, certain temperatures, or time. On the other hand, we have oscillation tests, where we apply only very small movements, which are typically not even visible with the eye, and they are not in one direction, but back and forth. So we do sinusoidal movements to the left and to the right at a certain frequency, and with very small amplitudes, and by that we get more structural information about the equilibrium structure of our sample. So in terms of battery slurries, we see here two typical examples. So both graphs show the same sample. So in blue we have an anode slurry made from natural graphite. In green we have one with a similar composition but made from a synthetic graphite. And in the flow test, as I said, we look at the viscosity change as function of shear rate. So we start here on the left side with very slow movements, where we get an indication of the sample behavior during storage, or the leveling behavior of the sample after the coating. When we increase the speed, so when we go more to the right, we see a decrease in the viscosity. So particles get oriented, network structures in the sample break up at higher speeds. So the viscosity decreases, and then at high speeds, we see we get information how the sample behaves under mixing or coating conditions. So from the flow test, we can get a lot of information for the processing and how the sample behaves during the processing. And on the right side, we have the oscillation tests, so small oscillation movements. Here we look at a different parameter, which is not called the viscosity, but a modulus, and we have not one, but two. So we have in blue the storage modulus, which is the elastic part. And so how much does the sample behave like a solid? And in green, we have the loss modulus, which is the viscous part, so showing how much does the sample behave like a liquid. And there we can, for example, see that for the natural graphite samples, so the one with the closed symbols, we have in total higher values. So something similar as we saw here also in the viscosity. But we can also see that here this crossover point shifts to higher frequency, which, for example, is an indication for a more stable network structure. So with the oscillation, we get information about the structure at rest of our sample. Impedance spectroscopy, on the other hand, also uses an oscillation technique. So here we apply an oscillating electrical voltage to our sample, and we measure the current. And this current is also sinusoidally and has the same frequency as our excitation potential, but it is phase shifted and it has a certain magnitude. And when we divide the voltage by the current, we get our measurement signal, which is the so-called impedance. We can look at this impedance of our sample as a function of frequency. And typically this is plotted in one or the other way. So one way is the so-called boat plot, which is here shown on the left. So where we plot either the magnitude of our impedance or the phase angle of the phase shift between current and potential as a function of the applied dielectric frequency. Or we can use the right side, so the so-called Nyquist plot, where we put the imaginary part of our impedance signal, the so-called reactance, as a function of the real part, the so-called resistance. And then for these curves, we get this typical behavior where we see first a half circle and then some increase at higher resistances. So we have now these two different methods, but by combining them, we want to get additional information that is not just possible by separate measurements. So of course, we can measure the impedance of the sample before and after shearing, but still we will not be able to know what's really actually happening during the procedure. And also, for example, if we look at, if we really produce the sample and code it on the current collector, then we cannot measure the slurry afterwards once it's coded. So somehow we need to simulate this coding process to get an idea of what's happening in the sample during processing, also on the electrical side. So that's why we want to combine these two methods together. And that's already a well-established technique. So there we also have some kind of a real dielectric setup, and this is something which is widely used in industry. So the main idea is that we have the two metal plates here in the center. These are the electrodes. So they are measurement plates for the rheology, but also electrodes for a capacitor to get the dielectric testing. And these electrodes are connected here through wires with an external LCR meter that applies the electric field. And on the other hand, they are combined through ceramic insulators with the rest of the rheometer so that we can do rheological tests. So the advantage of this setup is that we have plate-plate capacitor where we know all the electric fields very well. We have wired connections, which make it a very good electrical measurements, so we can get very sensitive dielectric data. It is also compatible with the furnace in our case. So this is the ideal setup for testing dielectric properties, for example, of polymers at elevated temperatures under mechanical stresses. But it has one big limitation, and that is the top geometry is connected to the LCR meter by wire. So this means that the top geometry is not really free to move. So especially if we think about the flow tests, where we have a continuous movement in one direction, especially at high shears, which are interesting for the coating process, the wire will not stand very long for those measurements. So basically, we cannot do flow tests with such a setup with wires while doing dielectric spectroscopy or impedance spectroscopy. But that's exactly what we want to do with the setup to get information about our slurry during production. So we need to come up with something different. And there are already other methods which either use liquid electrodes or spring connections between the top plate and the LCR meter. But both of these methods limit the impedance measurement, and they also add additional noise to the rheological measurements. So that is not the ideal solution. So in this case, we come up with something different, which is first used with a Peltier plate. So this is ideal for liquid samples. But then the unique feature is how we do or how we arrange the electrodes, because now the electrodes are not separated in the top and the bottom plate, but both electrodes are combined in the lower plate of this setup. So this means the lower plate is split in two halves, one connected to each electrode of the LCR meter, and they are separated by a ceramic insulator here in the center. Then with this setup, we can still use here wired connections between the electrodes and the LCR meter. So we still get a good or the best possible dielectric signal. But on the other hand, the top geometry is now not hindered in the movement in any way. So this means we still have no limitation of our rheological measurement. We have no additional friction, and we can do really high quality rheological measurements while at the same time doing high quality impedance measurements. Additionally, the whole setup is easy and fast to install, and it's made for liquid-like samples. So in the next few slides, I want to show you some of the examples how this material can be used. So here we have two different cathode slurries, which differ just in the load of carbon nanotubes. So we have one with 2% carbon nanotubes and one with 4%. And first we look at the rheology, which is plotted on the left side. So again, we see the viscosity of the two samples as function of the shear rate. And what we can see for both samples is that they have a high viscosity at low shear rates. So there's some kind of a network structure in the sample. When we increase the shear rate, the viscosity drops because the particles start to align within the flow direction until we reach here the coating behavior. And of course, the sample with a higher filler content, so with more carbon nanotubes, has a higher viscosity. But how does this affect the dielectric behavior of the sample? So what we did here is we have measured the dielectric spectra of the sample 3 times. So the first one is the blue curve, which is made at a very low shear rate. So in this case, 0.01 inverse seconds, so which is here at the very low end of the shear rate range. So this is to simulate the storage conditions of the slurry before we start to coat it. So right after mixing, we store it for some time, and we get, that's where we get this low shear dielectric spectra. And of course, we can see from comparing the top and the low graph, there is a significant difference between the two samples. The higher carbon nanotube loading, of course, has a much lower resistance, much lower reactance than the 2% CNT sample. But the important thing is what happens after the coating. So then we simulate the coating process. So we apply a very fast shearing that's here done at 1000 inverse seconds, which is the green spectra. So we can see during shearing, something is happening with our sample. And we change the structure of our carbon nanotube network. But now if we stop with the coating and we prepare our electrode for the drying, so the sample is at rest, We again measure it without any shear, so in a quiescent phase. That's the red curves. And there we can see, okay, for the 2% carbon nanotube sample, we go back to the original structure as it was before the coating. Whereas we see a significant difference between the blue and the red curve in the lower diagram for the 4% CNT sample. So that directly indicates that there is some significant change happening in the sample, right, due to the coating process. So this also means, for example, if we would just have made static dielectric measurements of the slurry right after mixing, in the case of the 2% CNT nanotubes, this might have given us the right indication. So that would also shown us the behavior of the sample after the coating. But for the 4% CNT sample, we would have maybe drawn completely wrong conclusions, because due to the coating process, the sample changed completely in its dielectric behavior, and we get a different response of the sample. So there it's important to combine these two methods with one another. Another example is here just the mixing process itself. So in this case, for these cathode slurries, we didn't vary the CNT content, but the solvent content. So we have 40% solid content and 50% solid content, and both mixtures were mixed with two different mixers. So one's a very mild vortex mixer and one a very rough planetary mixer. And if you look at the rheological data, so basically here in the small insides, there's the viscosity, always plotted as function of shear rate, and there we can see there's basically no difference between the two different mixing types. I mean, there is some slight differentiation here at low shear rates, but overall these curves look very much the same. But if we now go to the impedance data at under shear, so in this case at 2000 inverse seconds, we can clearly see that there is a significant difference both between the different loading situations, but we can also clearly differentiate which sample was mixed with which mixer. So there we can directly qualify the mixing process by impedance spectroscopy, so we can judge which mixing process gives us a better carbon black network, in this case, than the other mixing. And by that, improve the electrical properties of our slurry on an early stage. We can also do a time-dependent test with this setup, because of course also most of the slurries are thixotropic, so they need some time after shearing to go back to equilibrium structure. So here we tested a sample first again in a shear rate test, and then we took the dielectric spectra at different shear rates, and we can check how the sample changes there. And if we do this with a 3-step transient program, so we first apply a very low shear rate to simulate again the storage, then apply a high shear rate to simulate the coating, and again a low shear rate to simulate the resting of the sample. After the coating, we can see in the viscosity data that there's some time needed for the sample to recover to its original structure, and we can now collect during all these measurement times different dielectric spectra. And for a better comparison, I have now just put the data at 12 kilohertz from these spectra together. So that's what we will see on the next slide. So we have on the left now just the high shear region. So again, the viscosity, which is low but constant in the high shear region, and also the reactance at these 12 kilohertz is constant. But if we now go to the third step, so the low shear, to see the recovery of the sample. We can follow the increase of the viscosity, but also the increase in the reactance. And what we can see here is now that the increase in the reactance takes much longer than the increase in the viscosity. So if we would just have a look at the thixotropic behavior of the sample in terms of viscosity, we might think that after 40 seconds, everything is over, the sample is back in equilibrium, and now we can start with drying our electrode. But actually, for the conductive network, it takes more than 100 seconds to recover, or at least to almost recover to the equilibrium state. So there's still something happening in our conductive network, where in the rheology we still think everything is over now. So this can give us information about improving our production process. And here is the final example that I want to show you today. So here we have two completely identical slurries, and what was varied is just the supplier of the carbon nanotubes that were added to the slurry. And if we just look on the rheological differences, there we can see how the overall behavior of the sample is the same. We can see slurry 2 has a slightly higher viscosity, but in general, they are almost identical. So that might be acceptable in terms of quality control to say, okay, we can use also the CNT of supplier 2. But if we look at the dielectric spectroscopy at different shear rates, we can see a completely different behavior between the two slurries. So for slurry 1, there is no effect of the shear rate. So no matter if you shear the sample at very low rates of 0.01 inverse seconds or high rates up to 100 inverse seconds, the spectra or the Nyquist plot shows there's no difference between or in the electrical behavior. Whereas for slurry 2, we can see that with increasing shear rate during the test, these curves shift more here to higher resistances. So there is something happening in the structure of the carbon nanotubes during the shearing. And this was also proven if we after we have made electrodes out of these different slurries and took SEM pictures. There we can see a very dispersed network of the carbon nanotubes. And for the electrode 1, but for the sample made from the slurry 2, we see only bundled CNTs, which indicate a very bad conductive network. And in fact, if we test then a battery cell made out of these electrodes, we can also see that, especially when we apply a high current, the electrode 2 has very poor properties compared to electrode 1. So, but now the Rheo-Impedance assessor gives us the benefit that we do not have to go all the steps to the cells to do the final cell testing to judge, is this a good manufacturer of CNTs or a bad one? Right after mixing the first batch of the slurry and testing it in the Rheo-Impedance setup, we can judge, okay, slurry 1 is good, slurry 2 is bad. We might stay with the manufacturer 1. So I hope in this webinar I could give you an introduction to our new Rheo-Impedance setup, which has the unique feature of combining both electrodes in the lower plate, which gives you high quality impedance data, while at the same time the rheological measurement and the rheological capabilities are unaffected, so that you can really get structural insights onto electrode slurries under all processing conditions, and thereby detect changes in the properties of your final battery on a much earlier stage, saving you a lot of time and money in your research to find an even better electrode. And with this, I'm at the end of my talk. I thank you for your attention, and I'm open for questions.
Thank you, Lucas, for that great presentation. We will now take a look at questions. Please remember to continue to submit your questions through the question box. Our first question is, what is the upper limit for temperature on this device?
So the device is working with Peltier temperature control, so it works, I think, from 0 to 100 degrees. That's what I know out of my head, but it might even be a little bit higher. But so I need to check the exact numbers, but I think something like 0 to 100 degrees centigrade.
Fantastic. Our next question is, when you compare the rheology versus the impedance results, you were mostly showing viscosity curve from rheology tests. But will you be able to extract additional information from oscillatory tests that give you similar trend shown in impedance results, since modulus will also give information on the slurry network?
Yes, of course, you can also look at modulus and impedance at the same time, but to get modulus, you need to do oscillation testing. So an oscillation usually means you do small movements. So you do not really simulate oscillation processing. But of course, you can also do a 3-interval testing with oscillation, rotation, oscillation, and then look at the recovery with oscillation in rheology, and therefore at the storage and loss modulus and their time evolution, and at the same time do dielectrics. So this is also possible.
Our next question is, what's the quantity of slurry required for the measured?
So this is a typical parallel plate setup for rheometers with 40 millimeter diameter. So the sample volume is typically in the order of 1 to 2 milliliters per measurement.
And our final question is, would we be able to see change in the EIS when the cathode slurry gets over time or gels over time? Excuse me.
Yes, that would for sure be seen or show up in the dielectric spectra, but there's one big limitation, and that is whenever you have drying, so in your sample or the formation of the EIS, there might always be a volume change, and that might mean you need to change on one hand the distance between the two plates, so which also will affect the electric response, but also you might even lose the contact. So that is something you need to look closer at, but in general, yes, you would be able to follow these changes over time.
Well, thank you again, Dr. Lucas, and thank you again for joining us for our fourth and final webinar of this series. Please contact TA Instruments with any additional questions.